We need your every minute counts here. Okay, so I will talk about the SER6. Let me start with the first talk of the conference. So our current cosmological paradigm, right, is a universe that is expanding for 13.8 billion years, addressing for about 0.7 when it was half its current age. The expansion started to accelerate, and we attribute that acceleration in the simplest model to a component of the energy density that is constant, that we call lambda. That, together with the cold dark matter, is the lambda CDM model. Cold dark matter is responsible for growth of structure for the most part. This lambda CDM model, if you make some assumptions, has basically 6 parameters that once they are determined, they basically you know all the expansion and growth history forward. Okay, and the cornerstone of lambda CDM has been historically the CMB, I would say, that you see there. That has measured the power spectrum of density fluctuations in temperature and in polarization by WMAP first, then Planck, and recently IUCAA, SPT have done an amazing job because you see the measurements over a broad range of scales and the model there, which is lambda CDM. So they pin down these 6 parameters very well in lambda CDM. So the next question that we want to answer is, does lambda CDM holds across these 13 billion years of expansion? In particularly, as we get a lot larger and better data set at low redshift, typically from galaxy surveys. Okay? So that's one of the questions we want to answer. Does lambda CDM holds? And if it doesn't, what happens with extended models? And 2 parameters that I will be talking about, and I guess in the conference as well, for weak lensing. One that we consider very well, it's the variance of the density field in spheres of 8 megaparsecs. Okay? That is a measure of galaxy clustering, so very large variance means that things are very clustered. And the other is matter density, okay? Omega matter. So sigma 8 and omega matter are typically the things that we compare against the CMB, because that's what we measure very well. And in particular, for weak lensing is this combination. Okay? So in that context, DES was created 20 years ago, in 2005, roughly, precisely with the goal of constraining lambda CDM and dark energy, with 4 different proofs. So it's a multi-proof survey. I wanted to stress that. It does galaxy clusters with gravitational lensing, baryon acoustic oscillations, and supernovae. Okay? 3 of those proofs are final already, and results are in the archive. Final for the final data set. So clusters have published by analysis with midterm data. Okay, so DES is a photometric survey. Okay, it measures. It basically takes pictures of the sky in 5 imaging bands in the optical and in the near infrared. Okay, down to a magnitude of 24. So that means that it pictures the sky up to 10 times every position of the sky by the end of the survey. Okay. And it's in the south, it's 5,000 square degrees. And you see that a comparison of DES. This is this tank-shaped region compared to other surveys, some of which we will hear later, that as Euclid and LSST. It's a multi-proof survey, as I said before, because it measures weak gravitational lensing. Now the analysis that I show you has up to 140 million galaxies. That is the largest shape cutter that exists today, until Euclid releases the DR1. And then BAO from 16 million red galaxies, thanks to the large area. Okay, so we can do BAO because it's not a small patch on the sky. We can do supernovae because there are fields that are repeated with some cadence of 7 days and 2 magnitude deeper. So there are 30 square degrees in which you measure supernova and you identify supernovas photometrically. And there are galaxy clustering because there is a lot of synergies with SPT and the measuring cluster massive with weak lens. Okay. So 3 by 2, it's this particular combination, right? Remember, weak lensing is a shape distortions of galaxies in the background, the shape of galaxies in the background as their light travels through the large-scale structure. So galaxies are nearby. You can measure that distortion. Correlated, that is a direct test of cosmology. You can also measure galaxy positions and the correlation of positions. That's galaxy clustering. That has galaxy biasing in between, so it's not a direct proof of cosmology. But if you combine it with galaxy-galaxy lensing, which is correlation of shapes and positions, then you can access cosmology. And that's what we call 3x2, the combination of cosmic shear, galaxy clustering, and galaxy-galaxy lens. And it's the most robust thing that you can do in weak lensing, I would say. It is, however, a very complex pipeline, okay? Because you have to go through the definition of the catalogs, the redshift calibration. As I said, redshift are estimated photometrically. There are 3 papers that we put together for redshift calibrations, 3 types of simulations, inference, modeling choices, analysis choices, the measurements, and so on. So in total, this analysis, the final one, is we wrote 16 papers plus 3 cosmology papers. And I think that's pretty much the minimum you can do in number of papers. So it's intrinsically complex with many different moving graphs. Okay. So 2 things that we had, there were many new methodological advances in year 6. 2 that I will mention is measuring galaxy shear catalog. So as you see, the photons from galaxies, as I mentioned before, gets distorted through the large-scale structures as a gravitational deflection. That's what we want to measure, that's cosmic shear. But also by the instrument, by the atmosphere, by the detector, okay? All that adapts to systematics, multiplicative and additive systematics that you want to correct or understand from simulations. So in DES, you see there DES science verification, year 3 and year 6, all the different data releases that we have had. We had a new points per function that depends on color. That is what characterizes all the different distortions and noise that I mentioned in the previous slide. And basically, additive bias is much more control before. And a new algorithm to measure shapes, which is called meta-detection. Okay? That basically applies shears to images directly. So reduces the multiplicative bias in blended regions. Because the ESER6 is much fainter, so that was critical to reach this number of galaxies, so a number 140 million shapes from 100 million shapes in year 3. The density is about 8 from 5 before, and we'll jump to 30 in Euclid. And again, we go to this redshift. Okay. And in particular, this multiplicative bias that has a direct impact on your error bars has gone from 20 to 2, from year 3 to year 6. Okay, so it's a much better control. That is the shear catalog. The clustering catalog is called MACLIM. Okay, it's basically a magnitude limited sample whose cut is I band there. It's a magnitude limit that depends on redshift. So just to maximize the signal to noise and the constraining power. So basically, as you go from high redshift to low redshift, the sample becomes brighter and brighter because you have too many galaxies that you can just throw the ones that have worse photosynthesis, okay, and get the one. Galaxy clustering is a very high signal to noise measurement, so you only need 10 million galaxies and you are okay, compared to 150 for weak lens. The thing that is important for galaxy clustering, because galaxy clustering measures density fluctuation, so you really need to control the mean density across the sky, in particular because the observing conditions change from day to day. Okay, and over the year we have developed 2 different pipelines to control this kind of dependency that you see there. That is that the densities, the raw data, depends on the dust, on the stellar density, on atmospheric scene. Okay? So you need to remove these densities. We have built 2 pipelines. Now the correction that we are doing to our measurements is percent level only at high redshift. We have this. I will not talk much about photometric redshift. I have no time. But once we have the shear catalog and the clustering catalog, we split them in tomographic bins. 6 for the clustering catalog, 4 tomographic bins for the weak lensing catalog. Okay, 10 million galaxies and 150 million galaxies roughly. And then you do all the cross correlations, shape with shapes, position with position, galaxy-galaxy lens. Those are 50 cross correlations in total that you can build. And you see cosmic shear is the highest signal to noise measurement today. So these 50 cross correlations, as a function of, are basically correlations as a function of angle in the scale and also in different redshift. Okay? So really, and they are all covariant to some degree. So we really need to model all this in a consistent way. And you see the models there for lambda CDA. So how we do that? So we put all those measurements in a likelihood, and it's a massive inference problem, okay, in which we have of order 6, 7 cosmological parameters, or 8 in W0, W0. You have a lot of astrophysical parameters that are related to the modeling. Okay? Oops. So this is the data, the 50 cross-correlation mentioned before. The model has components like matter, nonlinear clustering, power spectrum, galaxy biasing, intrinsic alignments, baryon feedback. There are a number of parameters that you need to marginalize over. And then data calibration parameters. So in total, there are roughly 50 parameters you have to explore. And all the pipeline is tested on simulations and in synthetic data before you apply to blinded data. And then you apply to blinded data, you pass some thresholds that you want to make sure that your inference wants to satisfy. And then you unblind the data, the cosmology. I will skip that blinding part as well. Okay. So that's a bit of setting how the analysis is done, our catalogs, metric redshift, how measurements are done. For cosmology, let me start with lambda CDM. Okay. So this is constraints on omega matter, S8, which are the two parameters I will care about for the most part, from DES in pink, 3 by 2, and from a combination of Planck, ACT, and SPT in blue. Okay? So if you want, we cleanse in low redshift and then CMB at high redshift. And in the full parameter space, the two data sets are consistent to less than 2 sigma. In the 2D plane of these two parameters, they're consistent to 2.2 sigma, and then most of the difference is along the S8 direction, 2.6. But it's nothing very significant. Okay, so everything that is below 3 sigma, we don't think is significant. This is all DES. I said at the beginning, DES is a multi-proof experiment. So now this is combining all our 4 proofs for the first time. Okay, the combination of BAO and supernovae, these dashed dotted lines that constrain omega matter only, the combination of 3 by 2 and clusters. That combination is not final. The dotted lines are final. The brown one is not final, because cluster is not totally final. And the orange is all DES. Now the parameter difference with CMB in full parameter space has grown to 2.8 sigma, still less than 3, and mostly along the SA direction. This is an interesting plot. I think it's to a good extent the current peak, the end of stage 3 with cleansing, how the end of stage 3 with cleansing looks like, okay? Because it's showing other surveys. It's showing KITS, legacy. So this is cosmic shear final. That is in green. It's showing DSY6 in pink, same as before. Also cosmic shear only. And it's showing 3 by 2 from HSC, which is the other survey. And you see there is a level of variance. All of these are consistent with the CMB to less than 3 sigma. There is difference in the SA direction, systematically lower. KITS is the one that has the highest SA. DES is the one that has the most constraining. Okay, so that's how we enter stage 4 in a way. Okay, one more second, and I'll now, instead of talking just about DES, I'll combine DES with the most constraining other data sets that you can put together. Okay? So we have DES 3 by 2 in pink there, and then in green is what we call external low redshift, which is a combination of cluster abundance from SPT, DESI, DR2 BAOs, and supernova from DES. There are other supernova samples that you can use, and this picture will not just using the DES. Okay, so this is our best understanding of the low redshift, pink and green to some extent, and blue is the CMB as I showed before. The three are very complementary. If you combine the two low redshift proofs, it's the brown, and again, it's roughly 2.3 sigma with respect to the CMB in full parameter space in lambda CDM. Since this is formally consistent, you combine them, and this is our best understanding of lambda CDM in terms of parameters. The orange contours there, everything is measured to better than 1% with a neutrino mass with an upper bound. This is lambda CDM. If you look at WCDM, which is just, okay, I'll now let W vary, even though this WCDM is not an actual physical mode, okay? I just play the game of, okay, let W vary, what happens? And you recover a value for W that is consistent with -1 to 2%. Okay, so let me go to now extended models. We say, okay, now what happens if I let W have a evolution with redshift in the density? No? So we look at this W0, W0 lambda CDM model, which is basically letting W rather than being a constant, you have a time dependence, which is linear in the scale factor. Okay, this is what is called the CPL model, the CPL parametrization. These do map to some physical, actual physical model. Okay, and you see this is a result of the best fits. Okay, so in this W0, WA now, how do things look like? And the first thing here I want to stress is the yellow one. Okay, so the yellow one is just DES, all proof. So for the first time, a single mission with its own proof can constrain W0, WA to a figure of merit that is not a lot lower than just combining DESI and CMB. Okay? And it's a 2.2 sigma from lambda. Okay? Just from DES. And all these results are the main motivation in result from DESI at the March 2025 that shows this level of, that shows up to almost 4.2 sigma difference with respect to lambda CDM. So we wanted to explore this. So what we are playing now here is okay, so what if you put one data set out? Okay? Because what if this is just a result of some systematics that we don't understand? So the first thing you can do is you just remove CMB. Because originally, okay, these tendencies were shown to be probably caused by differences in omega matter between DESI and C. So you just remove CMB, all the ES plus DESI VAO, that is the green there, still is 2.3 sigma from lambda. And one thing to notice that to doing this green contour is critical to add 3/2. If you don't add 3/2, CMB plus supernova would be error bars that are similar to the yellow one. So adding 3/2 for low redshift test of the evolving dark energy is pretty important. The figure of merit is about 100. If you remove DESI at all completely, then again you have something that is 2.8 sigma. If you remove supernovae now, which is the most constraining, so there is nothing that dominates the error budget, but supernova is the one that contributes like 1/3 of the error budget. If you remove supernova completely, then you still land in this region of the bottom right panel. Okay? And there is a difference of 2.6. If you put everything together, it's 3 sigma. So this is our current best, I would say, test of the W0 WM model. Is roughly 3 sigma from lambda CDM. Is it significant or not? It depends when you ask. Certainly it's not a detection, but it's mildly, it's not, for us, it's not significant. It can change. The figure of merit is roughly 200. And the most interesting thing is that if whatever you remove, the significance doesn't change. It's always between 2 or 2.5 sigma. So it's really about the combination of data sets. And before closing, I'll show you those. So these are the constraints. And then something that you can do is to say, okay, rather than looking at W0, WA, which are the pivot points at redshift 0, which is very arbitrary. You can choose a pivot redshift just that W0 and W are uncorrelated, because these are correlated parameters, difficult to interpret. If you use a pivot redshift in which those two are uncorrelated, at the pivot redshift, you get that W is close to -1. And this is my final plot. And this explains why lambda CDM and WCDM works well, okay? Because it's not about the amplitude of W of C, but it's the time dependent. So all different combinations of data sets always return a pivot redshift value that is close to -1. Okay. So that was my last slide. Summary. I've gone through the methodology for DESI ER6. In lambda CDM, we have no significant parameter difference with CMB. In W not WA, neither. It's at the order of 3 sigma. So it's a perfect setting for stage 4 cosmology in a way, right? Because all this will certainly change in the future. I stop here.
You finished 5 minutes early.
Earlier?
Yes.
Okay, but I have 5 minutes for questions.
Yeah. Yes, so we have time for questions.
So the question is whether we see the concrete question. I mean, so the growth geometry split is being worked out at the current, so we don't know the answer to it. But we did growth geometry split in year 3, but I think we didn't explore W not WA. So I have to look at the paper to answer. But there is a paper on doing the result that I show you now is just an extension on W not WA. It's a 4 pages per paper, so there is a longer one coming.
Yeah, hello. Yes, so I have a very naive question. So, now if our dark energy is a dynamical dark energy, then we will have the perturbation equations for them as well. And if we go to the level of perturbations, will they have any effect on this galaxy shape and shape 2-point correlations? So if it is not a constant, then we can write Boltzmann equations for them as well at the level of perturbations. So, so will that have any effect on the shape, these 2-point correlation functions?
Yes,
so are they considered?
Yeah. So you mean if in these models, if there are growth perturbations, then they will affect the shear measure? Yes, exactly.
Okay, thanks. Are they considered in this?
No.
Okay, thanks.
I mean, you do account for the fact that the growth factor changes in
Exactly.
the W0 WSCDM.
But I thought, okay.
It's not just geometry. It's
No, I thought you meant for how we measure things and so on. Exactly. But the growth factor, it's accounts for this deviation, right? Everything is in the growth factor at this level.
Is there a base factor calculation between the WCDM and the lambda CDM model?
Is that?
A base factor?
Yes, we don't quote base factors because those are very dependent on priors and so on. But it's not clear. The phase factor is not, I can't dig out in the paper how much it is, but it's not very high. So it's not very significant.
The fact that this is speaking on some W not equal to -1 is not necessarily an indicator of preferred theory, right? Because if you have,
It's just that at this level of significance, the base factor is not a determinant.
So the W pivot of -1 or close to -1, was that by design or just?
No, precisely. That's not by design. So when you I think, no, I was going to show the picture. It's not by design, exactly. So when you, different data set combinations have different pivot redshift in which W0 and W8 are uncorrelated. So you pick one data set combination, you pick 3x2 plus BAO, for example, that gives you the pivot redshift and in which you can define this pivot scale, and you measure WP and you measure WA stays the same. It's just WP that changes, okay? And WP systematically gives you results consistent with -1 at this level. So it's not by construction, if that is the question.
Just a kind of related question is what you really think? What is your best, what's your interpretation of this? I mean, you seem to have shown pretty convincingly that there's about a 3 sigma tension with the flat lambda CDM, but then you kind of end with this issue that where W is best measured, it's actually -1. So you kind of, I mean, what's your conclusion?
That the difference with respect to lambda, it's really not in the overall amplitude of W of Z. The overall amplitude scale is -1. It's just in the time evolution. So we need to constrain time evolution.
Any other questions?
Thank you, Martin.
Yeah.
I wanted to ask, looking forward, let's say thinking about whether this can be approached something like 5 sigma, from the lensing side, have there been studied what it will take and what is the time scale of?
To get into
Getting-
5 sigma, just from
Particularly from the
lensing.
lensing side, let's say if you think about the Euclid, LSST and things like that, at what stage this will, assuming central point stays the same, at
Yes.
what point this noise will,
I think just from weak lensing, you will not get to 5 sigma. Yes. But this is proof combination.
no, I mean, keep this combination, but let's say I want to focus on improving the lensing studies, right? Which is going to happen with Euclid and LSST at some point. At what point have there been, from the lensing working group, have there been efforts to figure out what will be the level of noise to bring this down, keeping the CMB and galaxy clustering as it is?
Yes, exactly. Yes. Yeah, I'll show you the paper where that is. Yes, by the end of Euclid, we will have this 5
The
sigma.
full data of Euclid.
I would say so. Yeah. I can dig the exact numbers in the
Nothing
paper.
earlier.
So maybe one quick question from me. So what was the biggest challenge that you saw in the DS year, final year analysis?
The final year,
From the weak lensing side or from any of these cross-2PT analysis?
well, one of the biggest challenges is really communication and the fact that there are all this analysis is very complex and everything depends on everything else. And so there are many moving pieces and it's different to move forward coherently. Because there are all different groups producing results and my results depend on what you produce and so on.
Yeah.
So communication is
So one is like the personnel aspect of it, but the other one
The
is
technical, yeah.
like this in terms of systematics and so on.
I would say photosys probably. Yeah, these are photosys surveys, not weak lensing surveys. No, I mean, weak lensing is extremely hard, but there has been amazing advancements in the methodology. While for photosys, what we need is better data. We need better samples, and those data sets don't exist on. There is a ceiling that you cannot pass.
Thank you. So let's thank Martin again for this wonderful talk.
Thank you.